Okay, so maybe we can start. And so, hello everybody. Welcome to our GGI Tea Breaks. And let me say a few words about our speaker today, Brian Batell. So Brian got his PhD in Minnesota University. Then he made postdocs in Perimeter Institute, Chicago University, and at CERN. And now he's professor at Pittsburgh University. So Brian studies fundamental interaction. I think it's fair to say that you study fundamental interaction both at the energy and at the intensity frontier. And in fact, there has been a lot of activity and interest on the front of the intensity frontier recently, renewed interest, which led to design and study new facilities to with the aim of searching for example, long-lived particles, elusive and light new physics. And this led to, for example, to design new facilities like, for example, those at CERN are Matuzla, Codex B, and Phaser, just to name a few. And also there was a lot of effort put in initiatives like physics beyond colliders at CERN or the SNOMAS activity in the US. And much more. So there has been a lot of interest and activity on this front, just to go beyond the mainstream of studies which have to do with search of new physics at the energy frontier, which nowadays, of course, is at the LHC experiments. And Brian has been one of the main key players in these activities and this search for elusive new physics, and which can be in the form of dark sectors which are maybe very light and are elusive because they are very weakly interacting to the standard model visible sector. So I'm very happy to introduce and to give the stage to Brian. He's certainly an expert of this subject, and today he will tell us how to get inside into these dark sectors through portals. So please.
Well, thank you very much, Roberto, for the very nice introduction and for the invitation. It's really a pleasure to be able to give this talk and tell you about some of the exciting ideas related to dark sectors and portals, and as well as some of the ideas being advanced to experimentally search for these. So just in case this is not your main area of study and it's somewhat afar, the title maybe sounds a little bit like science fiction or out of a horror movie perhaps, but I can assure you that this is the jargon that's used by the practitioners, and soon we'll come to see what this exactly means. Okay, so just to start, I think many of you know this story, but I think it's a nice place to start with. So this is a picture of our universe by the Hubble Space Telescope. And of course, it's just one small little slice of the whole sky. And so the analogy that's often used is that if you took a sewing needle and you held it at arm's length and you looked through the hole, that would be roughly the fraction of the sky that you're seeing in this picture. And so if you count up all the galaxies in this picture, there's something like 10,000. Then we extrapolate to the whole sky. That means there's something like of order 100 billion to 1 trillion galaxies in our universe. Each galaxy contains something like 100 billion stars. And so this is some ridiculous number of stars in the universe, 10 to the 22, something like this. And we live on one planet next to one star and in one galaxy. And so it's just utterly ridiculous to comprehend. But the important point for this talk is that this is actually not even the majority of the stuff in the universe. And so this is the famous cosmic pie chart showing the energy budget of the universe. And so normal matter, stuff that makes up stars and galaxies, that's 5% of the matter in the universe. And we can study that and extrapolate to say very short distance scales. And from those studies, we can learn that normal matter is made out of electrons and nuclei, and we can do further experiments and learn that fundamental particles as we know them are described by the standard model of particle physics with the known strong electroweak interactions. So that's 5% of the universe, and then the other 95% of the universe we really don't really have a good idea about. It's not to say that we haven't made any progress over the years. So this is an earlier incarnation of the cosmic pie chart. This is a joke. I'm not sure if it is going across on Zoom, but anyway. Going back to our current understanding, I want to focus mostly on this talk on the idea of dark matter and what possible form it could take. Of course, the dark energy is a huge mystery. The simplest possibility is a cosmological constant. That of course leads to the cosmological constant problem. And that also may, in a very particular sense, have a solution in terms of many, many, many dark sectors, 10 to the 500 dark sectors, or something like this from an anthropic perspective. But I won't talk about dark energy for the rest of the talk. But dark matter, I think, is a fairly it's a difficult problem, but perhaps more tractable than dark energy. And that's what's going to motivate this talk for the most part, although I'll try to connect with some other puzzles later on. So all of the evidence that we have for dark matter comes from its gravitational effects. And there is a very wide, disparate range of effects, ranging from the velocity rotation curves in galaxies to the need for dark matter to seed structure in the early universe, from gravitational lensing effects, such as the famous bullet cluster, as well as precision studies of the temperature anisotropies in the cosmic microwave background. So all of this evidence is gravitational in nature, and I think one of the top questions today is whether or not dark matter has non-gravitational interactions. And the search for non-gravitational interactions is taking place in a variety of directions. I've just shown here some of the perhaps most popular or canonical ways to search for dark matter, particularly weak scale dark matter. So you could have direct detection of dark matter in our halo, in which dark matter scatters with the nucleus and you observe its recoil. You could look for the annihilation or decay products of dark matter, for example, in our galaxy. You could do collider experiments, such as at the LHC, and look for missing energy signatures. And there's a range of other possibilities, and some of them I'm going to discuss today. Now, I think a good question to ask when you start to study these types of experiments is there any good reason to expect dark matter to have non-gravitational interactions? And perhaps I think one of the best reasons is the need to understand the origin of dark matter in the early universe. We would have ultimately, if we discover dark matter, we would like to understand how it came to be in the early moments of the history of our universe. And so one possibility, a very simple possibility actually, is that dark matter could have been produced from particle reactions in the hot plasma during the Big Bang. And so you could have a Feynman diagram like this, where standard model particles in the bath scatter and produce dark matter particles. And in order to produce a sufficient number, this typically suggests a non-gravitational interaction with ordinary matter. And possibly the simplest idea is that dark matter is a thermal relic produced through what's called thermal freeze-out. And so here I've kind of outlined what that story is. And so at early times, at very high temperatures above the dark matter mass, both dark matter annihilation and production are efficient or in thermal equilibrium. And so you can think of the diagram as being efficient. It can go both ways, the scattering process. As the temperature drops below the dark matter mass, dark matter production will be kinematically disfavored. And so dark matter will begin to annihilate. And that's what you see on this plot. This shows the co-moving number density where we factored out the expansion rate. And you see that essentially once the temperature goes below the mass, there's exponentially decreasing number density. Eventually, this also freezes out because dark matter is becoming more dilute. And you're left over then with a relic population of dark matter particles. And so if you work out the details in this story, you find that the dark matter abundance is given by the correct value if you have a cross-section that's of order 1 picobarn. And 1 picobarn, as many of the experts in the audience will know, is characteristic of sort of a weak interaction cross-section. So you might ask then, well, we have this hypothesis of a non-gravitational interactions. What actually is going into this blob? Okay, what is mediating the interactions? And the simplest possibility is just the good old weak interactions that we're familiar with. So dark matter could be charged under the electroweak interactions, such as happens with a neutralino in the minimal supersymmetric standard model. And dark matter could be annihilating to W's and Z's. For this type of process, you find that you get the right annihilation rate and then the right relic density if dark matter has a mass that's close to the weak scale. And so this is a very interesting coincidence, and some call it a miracle or WIMP miracle. And I think it's especially interesting when you're motivated to think about dark matter near the weak scale, when you're motivated to think about new physics near the weak scale for other reasons. For example, the hierarchy problem certainly motivates such considerations. So this is a very interesting and well-motivated possibility, and has a very characteristic phenomenology. So you can take the same diagram that is responsible for producing the dark matter in the early universe, and you can look at it, the time direction in this diagram from various different perspectives, and that leads to these different possible phenomenological directions. So you can have dark matter scattering going in the upward direction with the standard model, that's direct detection. You can have indirect detection where dark matter annihilates the standard model particles. And then you can go the other way and have production at colliders. And so just to kind of give a snapshot of where we're at, if we, we can look at a nice figure of merit, which is the standard direct detection spin-independent scattering plot, which shows the WIMP mass on the x-axis and the WIMP nucleon cross-section on the y-axis. And over the past 25 years or so, we've made significant progress, and the limits on the cross-section keep marching down. And right now, I think the best limits are coming from the Xenon 1-ton experiment. And there's still some way to go until we reach the so-called neutrino floor, where we'll find, we'll start to observe background scattering events from solar neutrinos and atmospheric neutrinos and so on. But I think it's fair to say that so far we haven't found any, at least definitive signs of WIMPs. The WIMP framework is certainly well motivated. We should continue searching for WIMPs. But I think it's also time to open ourselves up to other possibilities. And I think a lot of the field is starting to do that, thinking about different theories of dark matter, as well as different experimental ways to search for such dark matter. And so what I want to ask is, what if dark matter does not experience the known forces of nature? By that, I mean the strong, the electroweak interactions. Of course, dark matter will experience gravity, but what if it doesn't experience the known forces of nature? And so this leads to the possible framework of a dark sector. And so, so here I just have separated the two things. So we have the standard model in one sector, that perhaps the dark matter is in another sector. There could be other things in this sector as well. It could be a very rich dark sector or a very simple one. You could have dark forces. You could have things like spontaneous symmetry breaking, confinement. if the standard model is a guide at all, then we might expect, there is some quite interesting and complex phenomena. Now, just by itself, it might not be so interesting. We might just have, the usual gravitational phenomena. But there is a possibility that this dark sector could still have a non-gravitational interaction and could couple to the standard model through what we call a portal interaction. So this will be some weak interaction that typically has a new mediator particle that interacts with both sectors. And this could lead to a variety of interesting effects, both for the dark matter cosmology and its phenomenology. Now, it turns out that given the standard model particle content and its symmetries, there are just a few possibilities for what are called renormalizable portal interactions. So these are operators where you take a gauge invariant standard model operator and you couple it to a standard model gauge singlet field that could be part of a dark sector. So there are these three possibilities. One is the vector portal, where we kinetically mix a new gauge boson, we call it a dark photon, with dark matter, with the ordinary photon. Another option is the neutrino portal, where we connect the LH gauge singlet operator to a singlet fermion. You could call this a right-handed neutrino or a heavy neutral lepton. And then the final possibility is the Higgs portal, where we couple a singlet scalar to the Higgs mass term. And so these are the three renormalizable portals present in the standard model. Of course, you could have also non-renormalizable operators. Other possibilities include you gauging certain anomaly-free symmetries in the standard model, things like B minus L. So there actually is a variety of different options, and I think physicists are now sort of systematically exploring all of the different portal options. And it's important to explore all of these. They all give their own distinct phenomenology, and so it's certainly worth exploring very broadly the possible non-gravitational interactions. But there are these three portals that kind of stand out in terms of their uniqueness and economy. So I'm going to mainly focus on these for the talk, and I'll give some examples in each class. You might think this is still a little bit speculative, exotic. Well, we can look back at history and sort of argue that this perhaps already happened. You could go back to the 1930s. Back then, we might say that the standard model was the theory of the photon, the electron, and the nucleons. And we observed this very interesting phenomena of beta decay. And so we can describe this essentially as a neutron decaying into a proton and an electron. But the novel feature, of course, was that there was a continuous energy spectrum. And so this seemingly violated conservation of energy. And of course, the solution was the neutrino. And in many ways, the neutrino is a good prototype for a dark sector. So the neutrino was electrically neutral, or a singlet under the electromagnetic symmetry. It's very weakly interacting in light. It interacts with the standard model through what we might call a portal. You can take the gauge singlet operator, coupling the neutron, proton, and electron to a singlet neutrino. So perhaps it's not too crazy to imagine that this could happen again. As it pertains to dark matter, another interesting thing that happens or opens up is that once we invoke these new singlet mediators, we can actually have much lighter thermal relic dark matter. So with just the ordinary weak interaction, there's a famous bound called the Lee Weinberg Bound, which essentially says that light thermal dark matter interacting through the weak interactions is generically overproduced. And you can understand this just by thinking of integrating out the Z. You're going to have an annihilation cross-section that goes like G Fermi squared times the dark matter mass squared. And so setting that equal to a picobar, and you find that if dark matter should be heavier than something like of order 1 GeV. If you have new light mediators in the game, such as these portal interactions, then you can very easily have much lighter thermal relic dark matter. And so here is a, just a very generic Z prime mediator. And if you work out the annihilation cross-section, you find that you could very easily have a cross-section of order 1 picobarn for even quite small couplings when the dark matter is well below 1 GeV. And so this perhaps focuses a little bit of the discussion on this lighter regime, say between the electron mass and the say GeV scale. And we'll see that in this regime, there's some new experimental approaches are needed to test dark matter of this type. Okay, so I want to turn now to a typical, or let's say canonical model of vector portal dark matter. And so I'll discuss this model a bit, and then I'm going to start to highlight some of the new experiments that are being done to try to search for such dark matter. Okay, so this model is quite simple. It consists of a new dark matter particle, a dark photon, which I'll call A prime. The dark photon mediates interactions between the dark matter and the Sander model. You can think of a diagram like a Feynman diagram like this. There are 4 parameters in this model: the dark matter mass, the dark photon mass, the dark gauge coupling, and the kinetic mixing parameter epsilon. And then we can, I'm going to show a few of these different plots in the subsequent slides. So this is a common parameter space that's used. This is on the x-axis, we have the dark matter mass. And on the y-axis, we have sort of an effective parameter that is characterizing the annihilation cross-section. You think of it as an effective coupling, if you like. And in this parameter space, we can draw a line where we get the right relic density. And that will serve as an interesting theory target for the various experiments. So along this black line, we get the right relic density. Okay, so one class of experiments that can be used to probe such dark matter are beam dump experiments. Here I'm going to talk about proton beam dump experiments, but similar things can be done with electron beam dumps. So the basic idea is very simple. You have a very intense proton beam impacting a fixed target or a beam dump. Out of those collisions, you produce dark matter. And then the dark matter is weakly interacting. It can travel through shielding or through dirt into a detector and then scatter with electrons or nuclei. And then you can look for those recoiling objects. This can be done with existing or near future neutrino experiments at accelerators. So experiments like T2K, Dune, and so on. In fact, this has already been used in the past to reinterpret past experiments and setting limits, as well as there has been one dedicated search. I'll discuss that in just a second. So in this simple model, how can we produce and detect the dark matter? So again, within the context of the dark photon model, there are several ways you can produce the dark matter in the proton target collisions. You could have, well, in the proton target collisions, you're going to produce quite a few hadrons, of course. So you could produce pions and eta mesons. Those could decay into a dark photon, and then the dark photon could subsequently decay into pairs of dark matter particles, such as in the first diagram. There's also proton Bremsstrahlung processes where you radiate a dark photon, and then it decays to dark matter particles. And then you could also have perturbative QCD production, such as QQ bar to dark photon. Once you produce the dark matter and it passes through the detector, it could scatter in various ways. And you could imagine it scatters elastically with electrons or nucleons. It could scatter through various inelastic processes as well. And so over the past several years, the theoretical description of these processes have been worked out and Monte Carlo codes have been generated. I'll just highlight one here by Patrick de Niverville, who was a collaborator of mine. And so following this proposal to search for dark matter in this way, the mini-boon neutrino experiment developed some interest in doing a search of this type. So mini boon, of course, it's a neutrino experiment. The basic way that they make neutrinos is to direct a proton onto a beryllium target. And out of those collisions, you make forward-going charged pions, which then decay to neutrinos in flight. So in this decay pipe. So you produce a large flux of neutrinos. Neutrinos could oscillate along the way and then scatter in the detector. For this particular dark matter run, there was a dedicated off-target run where the proton beam was steered past the target onto a beam dump. And this was useful in that it essentially removed this decay in flight neutrino production mechanism. And so the neutrino flux was significantly lower. And since neutrinos provide also a neutral current style background to the dark matter scattering process, this helped to enhance the dark matter signal. And so roughly a year-long run was carried out, collecting something like 10 to the 20 protons on target, and several searches were performed. And this particular analysis set the best limits on dark matter sort of in the order of 100 MeV range in this vector portal dark matter scenario. So this demonstrates that these beam dump style experiments can be used as an effective way to probe vector portal dark matter and other types of dark matter which can scatter with standard model particles. Going forward, we can imagine in the future at the Dune experiment doing a similar search, and this has been studied by several groups. Dune is uses a somewhat higher energy beam, and so could potentially probe somewhat heavier dark matter. Another interesting feature, at least under the current considerations of the Dune near detector, is that the near detector may be adjustable. You may be able to move it both on and off axis. And that can help to preferentially increase the dark matter to neutrino flux. So that's another way to deal with this neutrino background. So as we move off axis, the neutrinos, they're produced through decays of charged mesons, which are focused by a magnetic horn, whereas dark matter in these models, at least, are produced through the decay of unfocused neutral mesons. And so you can sort of see in this plot here, in the green, in the dashed green, as you go off axis, you can preferentially enhance the dark matter signal in comparison to the neutrino background. And so here is a plot in the parameter space of epsilon squared and the dark matter mass, showing that you can, Dune will potentially be able to extend the reach by up to 1 order of magnitude in the couplings, in the square of the coupling. Another idea that I've been thinking about more recently is to actually use the LHC, and not the main detectors, but looking in the far forward region. And I think the point here is that the LHC PP cross-section is actually enormous. So it's 100 millibarn, but it's mainly directed in the forward direction. And so what you have is essentially an enormous number of energetic, low PT light particles. So for example, you can have 10 to the 17 pions with TeV energies and Miller-Rade angles. And this has already been realized, and it's going to be exploited by the phaser experiment, even in run 3, to search for light, long-lived, weakly interacting particles. And in the past year or so, there's been further discussion and consideration of perhaps constructing a larger forward physics facility for the high luminosity era. And if you're interested in this, you can see that there was a kickoff workshop recently. I've put the link here. And so you can also use this, far forward and intense flux to search for light dark matter. And so the basic idea is that here you have, for example, the PP collisions in the Atlas interaction point. There's a very far forward flux of dark matter particles that are produced, and then the dark matter particles could pass through a suitable detector and scatter, for example, with electrons. So this is something I've been working with Jonathan Feng and Sebastian Trojanowski. The production and detection principles are essentially the same as they were in the proton beam dump experiments. You can produce them, for example, in pion decays, and then you could look for their scattering with electrons. We looked at two different possible detector designs. I think the details aren't too important for this talk, but one is the Phaser Nu2, which is an emulsion detector. And Phaser Nu also is an experiment that's been proposed and will be built to study neutrino interactions. This is an upgraded version for the high luminosity era. And then we also thought about a different technology, which is the so-called liquid argon time projection chamber technology. We found that you can use kinematic and topological cuts in these setups to mitigate the neutrino backgrounds. And so here is a plot that's sort of showing the reach, again, in this parameter space of Y versus the dark matter mass. And what you can see is by the blue line, if you follow the blue line, it can probe a fairly significant region of this thermal relic target in the sort of 10 to 100 MeV mass range. Okay, now I want to switch gears slightly and talk about another experimental concept which has some advantages in comparison to the beam dump approach. And that's the missing energy or missing momentum fixed target searches. And so the basic idea here is that you have sort of an active target in which you both produce the dark matter, but then detect the recoiling electron and measure its properties. And basically you can infer the presence of dark matter or some new physics by looking or measuring the momentum or energy. And so in this way, you don't have to pay the rescattering probability, okay, which is a fairly high price to pay. And so you're just basically sensitive to dark matter production. And there's an experiment going on at CERN right now, the Na64 experiment, that's using the missing energy concept. And so they use a 100 GeV electron beam incident on an electromagnetic calorimeter. And you essentially, in this dark photon model, you produce dark matter through electron Bremsstrahlung, so a process like this. You produce a dark photon and then it decays to dark matter particles, so you have a missing energy signature. So essentially they look for a very small energy deposition in the ecal, no energy deposition in their hadronic calorimeter behind this Vito. And they've already set limits based on a data set of something like 10 to the 11 electrons on target. And these actually do give the best limits in some regions of the parameter space. And future data sets with Na64 will probe a good portion of the cosmologically motivated parameter space. So for example, in the next run 3, they'll be able to collect something like 5 times 10 to the 12 electrons on target. That's this dashed line right here. And future data sets with both electron and actually muon beams can probe further into this parameter space. Another experiment now employing the missing momentum concept is the LDMX experiment, the light dark matter experiment at SLAC. So this is a proposed electron beam missing momentum experiment. And so they have essentially a thin target, and then in front of the target they have a tagging tracker. Behind the target they have a recoil tracker. And so this allows them to measure the momentum of the electron both before and after the dark matter is produced. And so essentially you have more kinematic handles to reject backgrounds, discriminate final state electrons and from photons. And so depending on the intensity of the beam, you can perhaps explore most of the thermal target parameter space. So for example, in the red line here, if we're talking about something like 10 to the 15 electrons on target with an HeV beam, you can probe a good portion of even the most pessimistic thermal target scenarios. Another approach is to use collider experiments. So here we're talking about medium energy electron positron collider experiments. And the advantage of these experiments is that they have large cross sections, high luminosities, hermetic detectors. So if we could have full event reconstruction. So in many ways, they're complementary to fixed target experiments. In this dark photon model, you can look for a missing energy signature, a monophoton signature. Babar has already done a search for this signature and placed the strongest limits on invisibly decaying dark photons in the 100 MeV to 1 GeV mass range. So that's shown by this green shaded region here. And of course, Bell 2 is now operating. They've already collected a significant amount of data. They hope to collect eventually something like 50 inverse attobarns of data, and they'll really be able to dig into this parameter space in the sort of higher mass end of this window. Okay, so now another topic which really deserves its completely separate, its own talk. I won't be able to cover it in any detail, is new ideas for the direct detection of sub-GeV dark matter. Now, traditional direct detection methods using nuclear recoils lose sensitivity to dark matter lighter than about 1 GeV. And so you can already see that on this xenon 1 ton limit plot. So going below, masses of order 10 GeV, you start to rapidly lose sensitivity. And that's just because light dark matter doesn't have enough kinetic energy to give the nucleus a substantial kick. And so there's a number of approaches to sub-GeV dark matter direct detection being pursued. There's dark matter electron scattering. There's dark matter nuclear scattering through a couple of novel effects, one called the Migdal effect, another which is the Bremsstrahlung effect. And there's also dark matter scattering off of collective modes in molecules and crystals. So I'm going to talk a little bit about the dark matter electron scattering just to give you sort of a flavor, but there is a lot of work, and I think, again, this is an area which is rapidly advancing. I expect to see a lot of new advances in the next 5 to 10 years. Okay, so just to give you a sense of the kinematics involved, so if we think first about the traditional method, dark matter nuclei scattering, the typical recoil energy is given by essentially the reduced mass squared times the dark matter velocity squared divided by the nucleus mass. And then just putting some numbers, say for sub-GeV dark matter, if we normalize the dark matter mass on 1 GeV and we take the xenon nucleus, we find that this recoil energy is of order 1 keV. So this is close to a typical threshold that is present in these experiments. And you can see that this scales as the dark matter mass squared. So as we lower the dark matter mass, we're getting even smaller recoils, and this is essentially why we lose sensitivity. Now, if we think about dark matter electron scattering, there's a couple of things to note. So one is we would like the dark matter kinetic energy to be larger than the binding energy, say to liberate an electron from an atom or excite it to the conduction band in the semiconductor. And so putting in the numbers, this would tell us that for sort of a typical electron volt binding energy, we would like the dark matter mass to be larger than 1 MeV. So it means we can potentially probe to much lower masses by examining dark matter electron scattering. We do need to have very low threshold, low noise detectors, and that can be seen by just looking at the typical recoil. So in the limit where the dark matter mass is heavier than the electron, you find that this is of order a few EV typically. And so it tells us that we would like to go to very low noise and very low threshold detectors. And so one detector along these lines, one technology along these lines that has already been put into practice is the Sensei experiment. This is a silicone skipper CCD detector sensitive to dark matter electron scattering. So the basic idea is that dark matter, you have sort of an array of pixels, many pixels, essentially made out of silicone. Dark matter comes in and scatters with an electron and excites it to the conduction band, and you have one or several electrons. And then the novel feature of the skipper CCD is that you have repeated sampling of the charge in each pixel. And then so that allows for a very precise measurement of the pixel charge. And so you have ultra low noise, and also you can then lower the threshold even to the 1 electron level. And so this has been already, again, put into practice. This is the limit from the Sensei at Minos run. It's a 2 gram, 24-day exposure run. So we're talking about gram scale detectors rather than ton scale detectors. And so this already sets the leading limits in sort of this 1 to 10 MeV mass range on the in the plane of the dark matter electron scattering cross-section and dark matter mass. This plot here is showing future projections for future silicon skipper CCD experiments, just based on different sizes essentially and different exposures. So 100 gram year, kilogram year, and 30 kilogram year. And so you can see that in terms of the cross-section, one can expect to push down several orders of magnitude. Okay, so I've talked a lot about the vector portal scenario. I want to switch gears a bit and discuss another scenario, which is the neutrino portal scenario. And so before discussing how we might incorporate dark matter into this scenario, I just want to first review the neutrino portal and the seesaw mechanism. So neutrinos, of course, have a tiny non-zero mass. We know once we add the neutrino portal, we add a singlet fermion to the standard model, we can write down the coupling, the LHN coupling, which is our neutrino portal. And since N is a singlet, we can also write down a mass term for the right-handed neutrino. And so this leads to a mass mixing matrix of the following form. And if you diagonalize that mass mixing matrix, you find the typical seesaw relations. So the light neutrino mass scales as 1 over m, the Majorana mass of the heavy neutrino. And so as you increase m, capital M, you will lower the light neutrino mass. This is why it's called the seesaw mechanism. And the heavy neutrino inherits the weak interaction of the ordinary neutrino through its mixing. Okay, so since you have mass mixing, it will inherit a coupling to the ordinary weak interaction, and it will be just the weak interaction suppressed by a mixing angle. Okay, so this type of mixing will govern a lot of the phenomenology of these heavy neutrinos. Now, building on that, it's natural to ask whether we can think of a dark matter scenario where the right-handed neutrino is a mediator to dark matter. And so this leads to the idea of neutrino portal dark matter. So the idea again is we have the LHN operator, and then N itself is a mediator to a dark sector. So it can couple to a dark matter field chi, a dark scalar phi. And then there are several different model implementations you might imagine. One interesting one is when you have an approximate lepton number symmetry, which allows for this Yukawa coupling to be quite large and in turn large mixing. So that leads to very interesting effects in cosmology and in phenomenology. In this scenario, some of the typical phenomenological features include essentially invisible sterile neutrinos. So you can see this basically as happening in the kinematic regime when the heavy neutrino is lighter than the dark sector particle masses. And so then the heavy neutrino would decay invisibly into a pair of dark matter particles and a light neutrino. And so this leads to a range of different phenomenological effects. So here what I'm showing is the sort of two-dimensional parameter space characterizing the neutrino, heavy neutrino and its mixing. And here I'm assuming just a single flavor dominance hypothesis. So either electron, muon, or tau flavor mixing. And then you can see there's a range of different phenomena. You can have modifications to the muon lifetime, which affects the prediction for the Fermi constant. You can have a non-unitary PMNS matrix. You can have effects in electric precision observables. You can have also searches for rare decays in muon, tau, and various meson decays. You can have invisible Z Higgs decays. You can have effects in Drell-Yan, as well as in oscillations. Now, in terms of the dark matter, this has a rather distinctive cosmology in the sense that we can now have dark matter annihilation into neutrinos, even with a thermal rate. Okay, so just like in the case of the vector portal scenario, I can characterize my annihilation cross-section in terms of some effective parameter y, which depends on the couplings and the mixing, as well as the dark sector masses. And then I can make a plot in the dark matter mass versus this y plane. And I'm not going to explain this plot. It's you know, a bit of a mess in some ways. We'd have to take some time to digest it. But just to say that basically, if I look at, say, this lower plane here, I have a prediction for the dark matter relic density along this solid line. And then there are, just like in the vector portal scenario, there's a variety of different experiments that one can compare this with. So I think in contrast to the vector portal scenario, this one hasn't been explored in as much detail. And so some parts of the parameter space still need some ideas to really, you know, try to probe those open regions. So I think more work on this would be, you know, very interesting. Now, so far I've really been discussing the cases when the mediator decays into the dark matter. But of course, there's other possibilities. One could imagine that the dark matter is somewhat heavier and actually gets its abundance by annihilating into the mediators themselves. So this is what's called secluded annihilation. And now in that case, the mediators themselves might decay back into the standard model visibly. And so you can really characterize the phenomenology in a very simple way in a two-dimensional parameter space. So basically, here are the three portal plots that we would have. We would have for the dark photon, we would plot the mass of the dark photon versus this kinetic mixing. And all the phenomenology would essentially be characterized on this particular plot. We could do the same with a visibly decaying heavy neutral lepton or heavy neutrino. So we have the mass of the heavy neutrino versus the mixed square of the mixing, as well as in the Higgs portal. So in the Higgs portal, we would have a mixing angle squared and then versus the scalar mass. Okay, so a lot of work there's been a ton of activity trying to characterize these very simple portal scenarios, and you know, a lot of new experiments have been proposed which could potentially probe these scenarios. I'm sure some of the ones are shown on these plots. Again, this is from the Physics Beyond Colliders report that Roberto mentioned at the opening. So I can refer you to that for more details. Let me just discuss since we haven't discussed it, let me discuss the scalar portal for a moment. So if we have the Higgs portal to a dark sector, and again, thinking about the case when the dark matter is somewhat heavier, so it's not really going to directly enter into the probes of the scalar itself, then it acts essentially just like a Higgs, but now with a different mass and a coupling suppressed by a mixing angle. Okay, so we can start off with this interaction, and then going to the mass basis, we'll find that the coupling is proportional to the mass of the standard model particle times some mixing angle. And so we can then work out, for example, its branching ratios, and we'll find that it will tend to decay dominantly to the heaviest particles. So for low mass scalars, it will decay to electrons. When we go above the dimuon threshold, it will start decaying to muons and then to hadrons and so on. And then the other key aspect of this type of phenomenology is its lifetime, its decay length. And so for relatively, even relatively modest mixing angles, something like 10 to the -3, 10 to the -2, we can already get scalars with macroscopic lifetimes. And so that leads to the suite of long-lived particle searches that are currently sort of a hot topic. So just to describe one experiment that I've sort of thought about, I'll talk about the DarkQuest experiment and how it can probe the Higgs portal. So DarkQuest, it's an experiment at Fermilab. It's actually a nuclear physics experiment. It uses 120 GeV protons from the Fermilab main injector, which impinge on a iron dump shown right here. And so the protons could come in and produce these Higgs portal scalars, and then they could travel and then decay into this instrumented region. There's a magnetic field here. There's also a muon tracking system. And the upgrade of this experiment is the idea is to install an electromagnetic calorimeter. And so you could, for example, look for dimuon pairs. The dark scalar can be produced in various different ways. You can have proton Bremsstrahlung, you can have gluon fusion, you can have kaon and B decays and so on. This plot shows the sort of the number of scalars produced, for a unit mixing angle in a given a certain amount of protons on target. And so just working out sort of the expected sensitivity, we find that DarkQuest really has quite good prospects to dig into some of this parameter space. So again, this is the mixing angle versus the scalar mass. We've outlined two possible phases of this experiment, one with 10 to the 18 protons on target, and one with 10 to the 20, and slightly different, decay regions, which would the experiment would be sensitive to. And so you can see that DarkQuest can cut into a range of this parameter space, and we can compare with other experiments. And you can see there's quite a lot of action in this type of model, just as was shown in the PBC plot. Okay, now, and just the last part of the talk, I want to just switch gears again. And it could be that dark sectors, of course, they're perhaps mostly motivated by dark matter, but it could be that they play a role in addressing other puzzles in nature. And so the one I want to discuss is the hierarchy problem. And so, in the last decade or so, there's been several proposals to address the hierarchy problem. You could say using portals and using dark sectors. So there's the twin Higgs scenario. There's the relaxion scenario, which uses the Higgs portal. There's also the n-naturalness scenario, which has sort of the number of copies of the standard model. So these are all, I think, very interesting ideas. And you could say that they sort of naturally fit within this idea, this very general idea of having a dark sector. Okay, so the twin Higgs is perhaps the first sort of scenario of this type, and it's really takes the idea of a dark sector to an extreme where we essentially postulate a full copy of the standard model, and it doesn't interact with our sector except through the Higgs portal interaction. And there are some technical details. There's a Z2 symmetry, which is used to enforce the equality of the Yukawa couplings and the gauge couplings in the two sectors. And that leads to a protection mechanism for our Higgs, okay? You could think of essentially this being caused in a way similar to supersymmetry. There are neutral top partners, and which sort of cancel the quadratic divergences. I'll note just for the moment that there is a small Z2 breaking that is required to actually implement this mechanism in a phenomenologically viable way, but that can be accommodated without too much difficulty. And so we could imagine that there's just sort of this so-called mirror symmetric spectrum where essentially we have exactly the same spectrum, although maybe it's shifted by a factor of a few due to the Z2 breaking. And so this would be a very rich dark sector, very, many different states, not quite like the ones I was discussing earlier, which were relatively simple. In this case, the phenomenology is dictated by the Higgs portal coupling. Okay, so and perhaps one of the main ways you would look for this is the precision test of the ordinary Higgs coupling to standard model particles that will be reduced by some mixing factor. And then you could also look for invisible decays of the Higgs into this mirror sector. Okay. Now, it could be, though, that this mirror sector is actually dramatically different. Okay, so even if in the UV they're exactly Z2 symmetric, you could imagine, and it's motivated to try to dynamically break the Z2 symmetry. One way you could do that is to imagine that you add some fields which also break gauge symmetries and simultaneously break the Z2 symmetry. Okay, so we could have a completely different pattern of gauge symmetry breaking in this mirror sector in comparison to the electroweak symmetry breaking we observe in our sector. And that's actually motivated in the sense that it can generate dynamically the Z2 breaking that you need to align the vacuum in the right way. Another interesting thing that happens in this scenario is that you can have new dynamical fermion mass terms. And so this could actually go towards realizing what's called the fraternal twin Higgs, when you have essentially tried to raise or remove some of the states from the spectrum. So just as an example, here I'm thinking about breaking hypercharge in the mirror sector, and you can now allow couplings of this hypercharged field to matter fields, and once the hypercharged field in the twin sector gets a VEV, that will generate new mass terms, and so you can marry the twin neutrinos to the twin charged leptons. You can marry the twin up quarks to the twin down quarks. And then you can raise those masses to some degree. And the interesting thing is in this scenario is that because of the Z2 symmetry, you can then have correlated effects in the visible sector. So if you have, for example, a Yukawa interaction which generates a mass in the twin sector, you could have a similar coupling in the a Z2 symmetric coupling in our sector, which then leads to various effects. For example, lepton flavor violation. Okay, so it's just to say that we could have a very symmetric mirror sector in such a scenario, or it could be actually quite different at low energies. And you could even think of dynamically breaking the color symmetries in the mirror sector, which could lead to a variety of interesting effects. For example, very low confinement scales in the dark sector. Okay, so I've tried to give an overview. I know that I haven't covered the subject exhaustively. It's quite a broad field by now, and there's some important things I think that I've certainly left out just for lack of time. But I do want to point out a few resources. So there's the Dark Sectors 2016 community report. There was a US Cosmic Visions New Ideas in Dark Matter report. There's the Physics Beyond Colliders Beyond the Standard Model Working Group report, as well as a US Department of Energy basic research needs for new dark matter experiments. So these might, if you're interested in learning more about this subject, I think these 4 references are a nice starting point to get going. Okay, so let me just end with a bit of outlook. So dark matter, I think, provides very strong empirical evidence for physics beyond the standard model. We don't really know at this point what dark matter is. There's many options, and I think right now the mode of operation is just that we're exploring as many options as we can and trying to think of new creative ways to probe dark matter. The cosmological origin of dark matter may provide a strong motivation for the non-gravitational interactions, and then we can then use those non-gravitational interactions to probe the dark sector. Dark sector paradigm is well motivated. It leads to a variety of phenomena associated with dark matter. Potentially there could be connections with other puzzles in nature, such as the hierarchy problem. We require new experimental strategies to probe these ideas, and as I mentioned, many ideas are being explored. And again, I've only sort of scratched the surface on this subject. There are very simple scenarios that I've outlined, but the dark sector could be much richer. And I think, again, scientists working in this field are really starting to explore those directions. So thanks very much, and happy to take some questions.
Thank you a lot, Brian, for this beautiful overview of searches and ways to search for these dark sectors. Now the session is open for questions and comments, so please raise your hand if you have questions or comments, and I'll try to unmute you. So I see one from Tanya, so let me try to unmute.
Yeah, can you hear me?
Yes, please go ahead.
Yeah, okay, thank you. So I think it's on slide 41 where I have the question. We don't have the slides, so I can. Yes, exactly. So for the bottom right plot, as an example, because I know this best, naively, I would assume if you have so low masses that you get constraints also from relic density. I mean, are they in here and I can't see them, or is there a reason?
Yeah, it's a good question. So, so in this particular slice of the parameter space, it really is sort of disconnected. There's not a direct connection with the dark matter story. So this is just assuming that there's for this plot, all you really need is, you postulate a scalar with a Higgs portal coupling, and then you're just looking at the phenomenology of that scalar. So the dark matter is somewhat disconnected. Now, on top of that, you could have, as I mentioned, let's see if I can go back right here. Yeah, so you could certainly couple then dark matter to this scalar. And in the scenario, in the parameter space that we were looking at in this plot, right in this corner, we would imagine then that dark matter is heavier than the scalar mass. So it would annihilate into scalars, and it would be governed by a different coupling. So you'd have some independent coupling here, say lambda or something.
I was reading.
And then you just adjust that coupling as needed to get the right relic density.
Okay, I was reading this. Can you go back to the slide we were just looking at?
So there would be probes of that. That coupling, I mean, for example, one way to probe that coupling would be to look at indirect detection. So dark matter is annihilating into scalars, and then they decay into standard model particles, and you could look for those with cosmic ray experiments, for example.
Okay, yeah, I was reading the plot wrong. I mean, this would be interesting, obviously, because my naive expectation would be that you get, depending on your additional couplings, but you get also some constraints then. Yeah,
you certainly would. So there is an interesting story, I think, along those lines. It's just that this portal phenomenology is really governed by the coupling of the mediator to the standard model in this case.
Okay, thank you.
Other questions, comments? Okay, I see another one. Please, Joseph, go ahead.
Hey, Brian, this is Joseph.
Hey, how are you?
Good, how are you? Great talk, thanks. My question is really, how do you see the prospect of LHCb discovering a portal, where portal also entails a certain lightness? What are your expectations there?
Sorry, say it again, a certain, well, LHCb.
Lightness.
I'm not sure if I got the complete gist of your question, but I mean, LHCb, I'm not sure if it's on this.
I'm basically referring to lepton flavor.
Yes. Okay. So
non-universality.
I mean, right now it looks very good, right? But yeah, I mean, I think it still remains to be seen. So, but yeah, I guess things like R sub k, for example, could fit within this framework. Although I think we also need, so scenarios that have been explored are things like L mu minus L tau. But on top of that, usually there needs to be also some, let's say UV physics, say above the weak scale, which generates couplings to quarks and so on. So there maybe some hybrid scenario could explain that. But yeah, I don't know. I mean, I think we just have to wait and get more data from LHC as well as Bell 2 to really see what happens. But yeah, right now it looks very exciting.
Yeah, as a comment, I could say that most of the efforts on for example, the model building point of view or the interpretation point of view has a focus on heavy new physics, right? So using the effective field theory approach, blah blah blah. So I think, in fact, I would be also very interested in seeing whether there is any proposal in the context of light, for example, dark sectors, and see whether this can work.
Yeah, I think there are. I mean, I'm not sure how light, but I think there have been some papers that have thought, for the ones I know about, maybe are like an L mu minus L tau gauge boson, which also has some coupling to quarks at the effective field theory level. Maybe it's generated by some mixing with vector quarks. I'm not an expert, but I think there has been some, certainly not as much as thinking about heavy new physics, TV scale new physics, but I think there have been some works along those lines, and I expect there'll be some more in the coming days. So
since we are talking about anomalies, let me enlarge the viewpoint and ask whether there could be any connection with the G-2 of the muon.
Yeah, that's a very good question. So, well, yeah, so I'm not sure if I have plots, but yeah, let me comment maybe on the case of like the dark photon. So you know, originally maybe say 10 years ago when a lot of this business was starting, you know, there was a open parameter space. We can kind of see it, you know, if we look at this plot right here, you know, there's some parameter space sort of at the level of 10 to the minus 3 or 10 to the minus 2 coupling, which and there's some band, right, where you would get the right correction positive shift to G minus 2 of the muon. And you know, at some point, you know, experiments were done and that possibility was ruled out for the case of dark photon decaying visibly. And then NA64, I think, put the nail in the coffin of the possibility that it was an invisibly decaying dark photon, if I can find that. So maybe again, I don't have the right plot, but you could have, yeah, like in this plot, again, you could have a, you know, epsilon versus MA prime, you could have a band for G minus 2. Mm-hmm. So another possibility that, and then so we just keep going a little bit to further model building. You know, you could have a dark matter scenario where you have inelastic dark matter. So in that case, it could be that some of the constraints from Babar would be evaded because maybe you have sort of a semi-visible decay. So the searches that they've done have not applied. So some people have explored that possibility. Or you could have just a mediator with different couplings. So for example, one thing I've looked at before is just a scalar that couples preferentially to muons. That's still a viable possibility, provided the scalar is heavier than twice the muon mass. And you know, Bell 2 will be able to make some headway into that as well as the LHC. So yeah, I think it's not, there still is room for light new physics to explain G minus 2, although some of the simplest possibilities have been ruled out.
Okay, thanks. Further questions, comments? Okay, I see one raised hand. So I'm from Anne. So let me unmute. Okay, please go ahead.
Well, hello, Brian, and
hello.
I'm Han. Well, I have a question about the detection of portals. Well, I want to say if it is possible for people to distinguish the such as the HNL signals between the neutrino signal in some neutrino detectors like ice cube or something else.
Well, yeah. So to distinguish the detection of neutrinos at ice cube from heavy, like did you say heavy neutral leptons or?
Yeah.
Well, neutrinos at I guess I haven't thought too much about this, but you know, at ice cube we're looking for, you know, high energy, ultra high energy neutrinos scattering. I suppose that in you know, perhaps in such events you could you know, produce other particles like perhaps heavy neutral lepton if it's light enough. Whereas in the types of experiments that I was discussing, these sort of intensity frontier experiments where you have you know, you produce heavy neutral leptons through you know, say heavy meson decays or you know, tau lepton decays, for example. You're looking then usually for like a long-lived particle signature. It really depends. You could also be a very prompt signature, for example, at Bell or at the LHC. So yeah, I don't know. Perhaps I'm just not an expert enough, but it seems like these are sort of different directions, not necessarily overlapping too much. But yeah, perhaps it's possible to also think of you know, perhaps producing a heavy neutral lepton in ice cube and then searching for it. I'm not sure if I addressed your question, but if there's anything I can clarify, please let me know.
Okay, thank you.
Okay, other questions or comments? Well, since I don't see any, let me ask, actually, let me make a comment, okay, and see whether there is any reaction on this. So it seems that at least most in your talk, in most of your talk, you focus on the case of marginal portals or even relevant ones, right? So don't you think, and in fact, in most of the studies, benchmarks are of this kind. I wonder whether it's worth studying and having a look also at irrelevant portals, cases in which the mediator is heavy.
Yeah. And, certainly it is, and I've done work on that myself. For example, this case of like this case we were just discussing of say a scalar coupled preferentially to muons. Really, you can't realize that with a renormalizable portal. You need to have some additional physics at the weak scale or higher to integrate out and generate, an effective operator of that type that would say give you something like a scalar coupled to Yukawa interaction. Another example that's well studied is the Axion or ALP portal. So I think these are very well motivated, and one should certainly investigate those. Maybe I think it's maybe sort of people are starting with the simplest cases in some sense, which are maybe the renormalizable ones. They're fairly unique set of minimal operators, and then maybe moving on. Although ALPs of course are even perhaps older than this whole portal idea, and those are also well studied.
How does the qualitative picture change? The picture that you gave, you for example, from these plots that we are seeing, so there is a message that we can infer. So how does this message can change?
Right. I think maybe the way to say it is that perhaps some experiments are better suited to probe one type of portal in comparison to another. So that's one aspect. So one or we don't even have to say portal, one model or one scenario than another, right? So you could even extend it to the case of adding dark matter to the picture. So I suppose there's a political aspect to it, which is, you want to ask like which experiment should be funded, right? And so, one part of that decision-making process is perhaps to compare, different models, how different experiments do, right? And so
exactly,
I suppose
because the relative importance between
but I don't know who decides, like,
can change.
Yeah, I'm not sure who would decide which portal is like the best portal. All of them can be motivated on different grounds. Like Neutrino Portal is motivated by neutrino masses. Vector Portal is maybe motivated by these thermal relic ideas. So I personally, I don't have a strong sense of, or strong intuition about which one is more likely to happen, right? I mean, so I think maybe the case would be made is like which experiments can maybe probe a variety of models, and so in that sense, it's good to look at models beyond just these three minimal portals. I think you don't get the full picture of all of the new physics that you might be able to explore by just focusing on these three models. So, I think you can see this also happening like in the physics beyond colliders exercise. So, they started with, a set of benchmark models, and I think now the exercise is continuing, and they're maybe adding some additional ones, to maybe get a more global picture of what's possible.
So I see another question from Nikita. Let's see, please go ahead.
Can you hear me?
Yes.
Well, it's a bit more technical, but I've seen that when you presented Lagrangian for the scalar model, there were two types of interactions, like triple coupling and quadric coupling. Are there any practical reasons to prefer one over another?
Well, I think in both cases you do get this minimal kind of mixing parameter, but on top of that you could have additional couplings, like a coupling of the scalar to the Higgs, which could be substantial depending on how you arrange these two couplings. So yeah, once you extend this, now it's instead of being let's say a 2-parameter model, it's going to be a 3-parameter model. So things like rare Higgs decays into scalars might be important. So yeah, there is some differences. There are some differences.
Mm-hmm.
Okay, is there any other question or comment? I don't see any, so I think it's time to thank our speaker again. So for this beautiful talk, I recall you that there will be slides and even the video recording available on our webpage, and there is also a Q&A way to interact with the speaker through the webpage. So please, I encourage you to use it. And so thanks again, and so see you